This is the University of Otago.
Good evening. My name is Harlene Hain, and I'm the Vice Chancellor here at the University of Otago, and it's my great pleasure to warmly welcome you to this inaugural professorial lecture. As with all of our lectures, it's fantastic to see staff and students from the University of Otago, but it's also fascinating to see members of the general public, and I would like to extend a very warm welcome to members of the Blakie family, particularly the children Blakie, which I assume are in the... excellent! Great. So we are so glad to have you here, and we join with you in your enthusiasm about your father's promotion. Like all professors here at the University of Otago, Professor Blakie has had to jump over some pretty large hoops in order to get to this point. But I think you will all agree, after listening to his lecture this evening, he has more than satisfied the criterion for promotion to professor. He has demonstrated very clearly his outstanding ability in research. He has a very long list of high-caliber publications. The citations of his work have climbed to over 1,000, and they grow by more than 150 citations each year. He's also the recipient of 3 highly coveted Marsden grants as a PI, which is an amazing feat for anyone. But in addition to his research caliber, Blair is also an outstanding teacher. He has taught across the entire curriculum from first year to fourth year level papers. He supervises postgraduate students and a large cadre of PhD students. He's the recipient of an OUSA Teaching Award, and the teaching evaluations by his students are uniformly extraordinarily high. But he's also excelled in service, and I think this is a really important area that sometimes we don't highlight at the beginning of these inaugural professorial lectures. He's excelled in traditional ways of high-level service. He's been on the Marsden Evaluation Panel. He's served on the Otago Research Grants Physical Sciences Panel. He's been the director of the Vulcan Computational Cluster at Otago and has served on the Otago NESI Steering Group. But I think the other thing that is really important to highlight here is that Professor Blakie has also participated in the communication of high-level science to members of the community. He's developed 2 NCEA curriculum posters that have been distributed to every high school in New Zealand. He ran the Physics After School program from 2004 to 2007. And he's a very frequent contributor to the Ask a Science forum that appears in many of the newspapers throughout New Zealand. So across all 3 areas at which we evaluate individuals for promotion to this rank, I think that you will all agree that he has clearly met and exceeded even our very strenuous University of Otago criteria. I would now like to call on the Pro-Vice Chancellor of Sciences, Professor Keith Hunter, to tell us just a little bit more about Blair's progress to professor.
Thank you, Vice Chancellor. And may I say again that this is one of the highlights of my job, introducing the new professors from science. Blair was born and raised in Inaugural, and in 1994 he came to the University of Otago, and he enrolled in a first-year program that simultaneously fulfilled the conditions of engineering intermediate, health science intermediate, and a BSc majoring in either physics or chemistry. Would that we could do that today. On February the 27th, 1995, at 9 a.m, he embarked on his quest to serve humanity by enrolling in the MB-CHB medicine program. At 10 o'clock on the same morning, he ended his quest to serve humanity and strolled over to the Science 3 building where Jerry Carrington, I imagine gratefully, enrolled him in an honours program in physics. Blair confesses that he actually preferred chemistry, and I'm not surprised at that, but he had an inability to perform experiments, which I can attest is somewhat of an impediment to studying chemistry. During his physics degree, He was a scholarship holder from the New Zealand Aluminium Smelters Company, and for 3 summers he worked at the Tiwai Point smelter. Now, the smelter had a policy of placing university students in parts of the organisation where they could best use their skills. So as a physics student, he worked 12-hour shifts in the rodding room. And the rodding room is where you use a sledgehammer and a crowbar to break slag off the anodes or rods so that can be reused. In 1998, he had completed his degree and he began a PhD, again at Otago, under the supervision of Rob Bella, with considerable input from Crispin Gardner, who at the time was a self-employed physicist in Wellington, and who later came to the University of Otago. He completed his PhD in 2001, with the title of his thesis being Optical Manipulation of a Bose-Einstein Condensate. After that, he went on a postdoctoral fellowship at the National Institute of Standards and Technology, or NIST, in Maryland, and he arrived in the USA only a few weeks before 9/11, and he also lived in the neighbourhood that was tormented by the Washington sniper. As well as that, NIST also had a number of suspected anthrax letters delivered while he was there. So not surprisingly, Blair got out of Maryland and took up a lectureship at Otago in 2004, where he has remained ever since. So Blair, my congratulations on your thoroughly deserved promotion to Professor, and I invite you to deliver your inaugural lecture.
Okay, good evening, and thank you for the very kind introduction. It's my pleasure tonight to tell you a little bit about things that interest me. The title of my talk is Ultra Cool Quantum Physics. So, what I want to do is take us down to some of the coldest stuff in the universe. I'm going to start by exploring the cold, and in Dunedin it's very easy to explore the cold. And I was hoping that it being May in Dunedin would dish up a day today that would impress upon you how cold it can be. But it's actually a fantastic day, although just turning recently. So what I want to start out by doing is just wandering through down into the cold to see what lies there. Now, temperature is a way of characterizing how cold something is. Temperature is a very subtle concept in physics and actually very hard to define. But everyone in this room understands what temperature is incredibly well. And for instance, I know many people put a lot of effort at the moment into insulating the houses, gathering fuel for the cold winter approaching, etc. We all want to exist at this comfortable state of 20 degrees Celsius plus or minus. And we all know how terribly cold and horrendous it is to be in these situations where it's a little bit colder, like I've said here, the Scarfy Flat at approximately 0 degrees Celsius. We could not think of anything worse than that. So this, perhaps our first impression is cold is sort of boring and uncomfortable. I hope to change your mind about that tonight. If I ask you, what is the coldest stuff you can think of? Well, if you were to wander around parts of the university, you might see people filling up these containers with liquid nitrogen. You may also encounter this stuff if you go to your doctor. Liquid nitrogen is really, really cold stuff. It has a temperature of negative 196 degrees Celsius. That's the temperature at which this boils. That is really cold. It was first liquefied in 1883. But actually, I should make one point here. In physics, we don't like these negatives, negative temperature. That's not a very useful concept, and it really shows us the breakdown of the Celsius scale. So from this point on, I'm going to refer to things in the Kelvin, or absolute temperature scale. In Kelvin, the unit of Kelvin is the same size as a degree Celsius, except it starts from absolute zero, where everything stops, which is negative 273 degrees Celsius. So on this new thermometer here, I've plotted what room temperature is, about 293 degrees Kelvin. And you can see that we've decreased all the way down to about 77 Kelvin, where nitrogen or air becomes a liquid. Okay, so that's pretty cold stuff. life actually already gets interesting when we get to this sort of temperature regime. There are things we can find in this regime, such as superconductors. This is the first of the super phenomenon we will meet tonight. What is a superconductor? It is a material which has zero resistance to electrical current. Most materials, you run electrical current through them, they get warm. A superconductor has zero resistance. That means if you make a loop of wire and you set up a current and it is superconducting, that current will continue without any battery forever. That is really a super phenomena. Well, superconductors were first discovered in about 1911 in materials such as mercury at extremely cold temperatures of about 4 Kelvin. As time has progressed, the temperature at which these systems become superconducting, that's a phase transition to the superconducting state, has gradually increased as people have found better materials. And in particular, on this graph down here, showing the sort of history of these superconductors, around the 80s, there's a sudden jump up to materials that are superconducting at liquid nitrogen temperatures. So these are the so-called high-temperature superconductors, the cuprates. So this is some fun you get down in these cold temperatures, wonderful phenomena like superconductivity. We can go a bit colder. Helium's a really wonderful element. Helium becomes a liquid at 4 Kelvin. And it's a really interesting substance because it is so light that helium does not become a solid. It's the only substance we know of that doesn't become a solid as you decrease the temperature to 0. It becomes a liquid, but that is it. So helium's a really interesting material, and I'll talk about it a few times. Its boiling point is 4.2 Kelvin. That is really cold. Most people will not encounter this stuff. It is very rare and expensive. I've shown a picture here of a gentleman loading up some helium, liquid helium, into these units, which are part of MRI machines. It's used to make these superconducting magnets required to take MRI images. So this is really cold stuff, 4 Kelvin. Look how much colder is on my thermometer than liquid nitrogen, and that's really cold stuff. So we're going right down now to these, getting pretty close to 0 here. Let's go a little bit further. We can ask ourselves, what's the coldest naturally occurring temperature in the universe? Actually, it's only a little bit lower than that. At 2.7 Kelvin is the average temperature of the universe far away from things such as stars. This is the temperature of the cosmic microwave background that flows through our universe. This is a picture of the fluctuations on that background of radiation. So this is what we expect to be the lowest naturally occurring temperatures in the universe. It is really cold, 2.7 Kelvin. This is extraordinarily cold. I can go half a Kelvin below that and something interesting happens. Helium became a liquid at 4 Kelvin. I go down to 2.2 Kelvin. Helium undergoes a phase transition. It becomes a so-called superfluid. Superfluids are really exciting fluids. They do strange things. They flow with 0 viscosity. So like a superconductor current flowing with 0 resistance and a superfluid, we have the flow of a fluid with 0 viscosity. That leads to odd things. Films in helium will climb up out of their container to lower their potential energy. That is really odd. The scientists first working with this basically needed their heads read after seeing what this fluid did. It has 0 viscosity. That's no friction. It can flow through porous plugs that would normally hold any viscous fluid. This is really odd stuff. It was discovered in 1937, and there's something else really odd about this. Helium comes in 2 isotopes. Isotopes basically are the same atom, but they differ in that there's one extra or a different number of neutrons in the nucleus. Now, normally we don't care so much about that. Different numbers of neutrons in the nucleus would affect nuclear reactions. You might care about it if you want to build some sort of nasty nuclear weapon, but usually at a chemical level there is no difference. But here is the mystery. Helium-4, the isotope of helium that weighs a little bit more, becomes the superfluid. Helium-3 does not. So normally, almost no difference between these, but here the sudden difference. This occurs, this beautiful superfluid transition, 2.17 Kelvin. Well, if we go a bit colder, something will happen to helium-3. In fact, at 1,000th of a Kelvin above absolute 0, helium-3, the other isotope, finally becomes a superfluid. This is really cold. It was discovered 40 years later in 1972. A really odd phase of matter. Now, I've upgraded my thermometer. I've got a golden thermometer. This is a logarithmic thermometer. I need that to see what's happening. I've got way down below a Kelvin, and to resolve what's happening, I need to use this. Now, look at those landmarks along the way, room temperature down to liquid nitrogen. Oh, there was hardly anything on this thermometer. The biggest jump to date has been from where helium-4 becomes a superfluid down to this super cold temperature where helium-3. So we're left with some questions. What is the origin of these super phenomena, superconductivity, superfluidity? Why is there a colossal difference between the behavior of helium-3 and helium-4? These are two deep and very interesting questions we can hope to address. So, where does the answer reside? The answer to this question comes from one of the most successful theories of modern physics, the theory of quantum mechanics. Now, quantum mechanics is a wonderful subject. It's got a cult following. Normally, we sort of teach this over 3 or 4 years. Over many papers, we rely on our friends in the maths department to do a lot of teaching that helps our students get appropriate skills as well. Quantum mechanics takes a long time to learn. However, in order for us to understand what's going on, you're going to need to learn it, so I'm going to give you quantum mechanics. I'm going to compress 4 years down to a couple of slides. Quantum mechanics rule number 1. Basically, you could say this is Heisenberg's uncertainty relationship. Heisenberg's uncertainty relationship states you cannot precisely know both the position and momentum of a particle. So we are not allowed to say this particle is here and it is doing this. That is illegal. That is not consistent with how nature actually is at the microscopic level. That's only something that's a good approximation for large objects. So we need a different description. That description comes in terms of these things called wave functions. That is how nature is at this microscopic level. And so here I have, for reference, shown a box, in this case a potential, and I've drawn some wave functions inside of it. Interesting thing about this is these wave functions describe the allowable states of a particle in this box, and they appear at discrete or quantized energy. So this is how quantum mechanics describes what you're allowed to do as a particle really. So this is quantum mechanics rule 1. Quantum mechanics rule 2. We start this in late 3rd year into 4th year, so we're halfway through a degree now. Identical particles are indistinguishable. What do I mean by an identical particle? 2 electrons, 2 neutrons, 2 protons, 2 hydrogen atoms of the same isotope. 2 identical particles are indistinguishable. What I mean by that is they are fundamentally indistinguishable. It's not that we're not good enough scientists to measure this difference. Nature itself cannot tell the difference if you swap them around. This is a very curious feature of the world we live in. Furthermore, fundamental particles come in 2 flavors, 2 types, 2 categories, fermions and bosons. Of course, there's been a lot of attention to bosons in recent years because of the Higgs boson. So let me tell you a little bit about what these 2 families are. For fermions, the elementary particles are probably things you've heard of. Things such as electrons, neutrons, protons. These are the elements we build up atoms out of. The elementary particles of bosons are perhaps a little bit less familiar. Photons. These are the particles associated with light, and the other elementary force particles. What's the difference between these 2 categories? Well, they have different rules about how we can use these particles. For fermions, the so-called Pauli exclusion principle applies, that there can be at most 1 fermion per level. So you start to put lots of atoms or lots of particles in a system. In the case of fermions, you're only allowed to put 1 in each of those levels. In the case of bosons, there is no restriction. You can have any number of bosons in each of those available levels. Now, I should say I've talked about the elementary particles. You can build up larger particles, atoms, for instance, out of these. And these so-called composite particles are also categorized as bosons or fermions. And the rule is basically the following. If you have an odd number of fermions in you, an odd number of neutrons plus protons plus electrons in your atom, it is still a fermion. So, for instance, helium-3 has an odd number. On the other hand, if you have an even number, such as helium-4 with one extra neutron, you are a boson. So let's ask ourselves, if we go to extremely low temperatures, when you remove all the energy from a system, it's going to try and settle down to be in the lowest energy possible configuration it can have. For the case of bosons, here I've shown 5 bosons, 5 blue bosons. The lowest energy configuration is I put all 5 in the lowest state. That's very nice. This is known as a Bose-Einstein condensate. It's a very simple state. It's predicted by Bose and Einstein in 1925. On the other hand, if I had fermions, I'm only allowed, by the exclusion principle, 1 fermion in each state, and so my lowest energy ground state is by stacking up these particles. And so I've shown that on the right there. 2 very different states, only differing because one of these, so I've used the example of helium-3 and helium-4, they only differ by something very small in the nucleus, but leads to this very large difference in how they behave. So in some sense, we now have a resolution to the difference between these systems. So questions relating to why they become superfluid, etc. So helium-4 becomes a Bose-Einstein condensate at 4.2 Kelvin. That's why it becomes a superfluid. Helium-3 is not allowed to. It's fermionic. But something does happen 2,000 times colder. Those helium-3 atoms sort of make a little molecule. And those molecules are bosonic, then they can condense. So it's this pairing operation between the helium-3 to make them into bosons that allows them eventually to become a superfluid. This pairing procedure is very similar to what happens in a superconductor, where electrons pair up and then they condense. So actually this idea of condensation of bosons underlies these super phenomena. So this is why this Bose-Einstein condensate is very important phenomena at cold temperatures. Well, a few confessions. That's a little bit overly simplified. Liquid helium is a dense and strongly interacting system. That means that there's a few bad things coming out of this. The interactions deplete the condensate. Even if you could take helium, superfluid helium, down to 0 temperature, the condensate would be less than 8% of the system. Interactions basically destroy it. They promote 92% of the atoms out of the condensate. The theory is extremely difficult. This is a dense liquid. The atoms in the system are basically touching each other. It is a very dense and difficult to model system, and the experiments are hard. The holy grail has been to obtain a dilute gas condensate. This is a system that is so dilute the interactions do not disguise the condensate. We can have a condensate of effectively 100% and see Bose and Einstein's original prediction. However, if I have a dilute gas, I lower its density. Its density is a lot lower than a liquid. And what happens is the critical temperature at which we get this Bose-Einstein condensate is lowered to incredibly low temperatures, in fact, into the regime of the ultra-cold. That is less than a millionth, and I mean less than a millionth of a degree above absolute zero. These are extraordinarily cold temperatures. Of course, I wouldn't have raised it had it not been possible. And a few very important developments in the area of atomic, molecular, and optical physics have enabled us to get into these regimes. Now, I'll emphasize I'm a theorist, so I think about this rather than doing it, but I'll take you on the journey of what competent people do in the labs. Okay, so one of the procedures for getting down most of the way is to use this procedure known as laser cooling. One takes your gas, isolated in some sort of vacuum chamber, and there's a nice little picture here of this dot showing a little sample of gas. You shine in appropriate lasers from all directions, and they can actually reduce the temperature of this gas from something of order room temperature down to of order tens or 100 millionths above absolute zero on the Kelvin scale. How is this done? Well, it's a long story and a little bit long to tell here, but essentially, photons in the lasers carry momentum. They can collide with the atoms and they can remove its velocity. And if you collide enough photons with the atoms, you can cool it down to this regime. Now, this amazing technology was developed in the late 70s, 80s, and 90s, resulted in the Nobel Prize in 1997. Of course, we had Bill Phillips here giving a public lecture at the start of last year about this amazing achievement. You may also recognize Steve Chu, who until recently was the Secretary of Energy in the United States. Okay, so that's really cold, but it's not cold enough. You won't get a condensate with laser cooling. You need to go a lot colder. One needs to use a second technique. It's known as evaporative cooling. And evaporative cooling, well, this is actually something everyone in this room knows about. When you get a hot bowl of soup, and taking a spoon, what you do is you blow upon the spoon, removing the hot atoms of steam, and the soup in the spoon gets colder. Now, with a 5-year-old and a 4-year-old at home, I spend a large fraction of my time evaporative cooling, so I've got very good at this. And so in experiments, how it's done is, well, there's some sort of trap holding these atoms. This could be optical, this could be magnetic. Only the hottest atoms run up the side of the trap. And if you can lower the sides somehow, let those atoms escape, they will take away an above average amount of energy, hence reducing the temperature. Now, normally when you evaporatively cool and you blow upon a spoon of soup, you probably don't notice that the soup goes down, unless you blow so hard it spills over the side. But normally you wouldn't actually notice the amount of loss. But in the evaporative cooling they perform here, they probably throw away 99.9% of the atoms. That's an amazing way to lower your temperature. And so that's how we get from tens or hundreds of millionths of Kelvin down to the nano-Kelvin regime. Okay. So this technique is very useful, and this led to the observation of Bose-Einstein condensation. 70 years after Einstein predicted it, this was realized in the lab. 2 labs in the US realized this in 1995. The group at Boulder, Colorado, with rubidium-87, a bosonic isotope. And later that year, the group at MIT with sodium-23, another bosonic isotope. And so these famous pictures show something kind of interesting about this phase transition. And I emphasize that these pictures are taken by releasing the atoms from the trap they're in. They expand out, and these pictures really show you the velocity distribution of these systems. And they're taken by shining some laser on the atoms and taking a picture of the shadow. I want to emphasize that you take a picture of these atoms, you destroy them. They are so cold, you take a picture, they are gone. Gone in the sense of heated up. So moving from left to right in both sets of pictures, what we see is the first picture on the left is the velocity distribution before you have a condensate. This is an isotropic, basically normal gas of atoms. You cool it a little bit, and this big peak develops in the center. This is the Bose-Einstein condensate waving, hello, here I am. This is a macroscopic number of atoms, where I mean 10,000. A macroscopic number of atoms, all in a single quantum state. This is a phenomenal state of matter. And then the rightmost graph is almost a pure 100%, all the atoms in a single quantum mode. This is our quantum fluid. This was an amazing achievement that really revolutionized this area of physics and resulted in the 2001 Nobel Prize to these 3 gentlemen. So now I want to convince you, okay, this stuff's really cold. This is in the nano-Kelvin regime. This is 1 billion times colder than anything else you'll find in the universe. That is really cold. Okay, but it's really interesting. This stuff can do some weird stuff. And let me show you a couple of experiments that were very important for me. Well, I think are very important. One was an experiment done soon after the first realization of BEC, and it was to take 2 condensates, separated in space a little bit, release them from their traps, let them expand and overlap. The question is, what happens to the system? And we have these images on the right, perhaps concentrate on the experimental ones, and they show that in the region where they overlap, there was some interference fringes. Well, this should bother you because here I had my 2 BECs expanding and overlapping. So if I think about the density in that region, some densities flowed in from one of these condensates, some densities flowed in from the other. They should just add up. But actually what this picture shows us is that instead of them just adding up to twice the density, we have regions where we added atoms on top of atoms and they cancelled out. There's nothing there. We have other regions where we added atoms to atoms and there's twice as much as you expect. If this doesn't bother you, something is wrong with you. If you know quantum mechanics, you should be able to predict this, but it should still bother you. This is a quantum mechanical matter wave. This is a phase of matter unlike anything we have intuition for. Okay? This is why it's worth going down to these ultra-cold temperatures. Here's another very important experiment. When I moved to NIST to do my postdoc, I joined a very big group of theorists and experimentalists concerned with making optical lattices to do this. A group in Germany bet the experiments there, but this was a very important experiment that was followed on by many other groups around the world. So let me tell you about this experiment. What one wants to do is make an interesting container to hold your atoms. And I think this shows you the amount of flexibility and how much fun we can have in this field. This interesting container is to make a lattice, a periodic potential. Another way to say that is I want to make something like an egg carton for holding atoms. We can do that by interfering pairs of light fields, laser fields, to make standing waves, and the atoms see that like a potential. So it's very precisely engineered egg carton potential to put your atoms in. The reason why this system's kind of interesting is that when your lattice, you're holding them in, is shallow, your intensity of your lasers is quite low, what happens is your condensate spreads out through the whole lattice. This is kind of interesting. Firstly, the atoms don't have enough energy to get over the barriers. So the reason they spread out through the lattice is quantum mechanical tunneling. That's a nice and interesting feature. But nevertheless, each atom is in a wave function that spreads out over this whole system. If you suddenly release it from the system and watch what you get interference pattern again, just like we explained before. But here's the curious thing. This is a dilute system, extremely dilute. You might think interactions aren't important. Actually, we can engineer them to be as important as we want. And as the depth of this lattice increases, what happens is interactions fight tunneling, and the system undergoes a phase transition to a new phase with precisely one atom per site. This is no longer a system with all the atoms in the same state that become strongly correlated. So by just controlling the intensity of the lasers or the lattice depth, you can engineer this transition between two distinct phases of matter. And of course, luckily, if you lower the lattice, you'll get back your old interference pattern. This is a reversible, what's known as a quantum phase transition. This experiment pulled in a huge number of people to our field who previously thought this was just a cute little field. Part of the reasons is this mod insulator state looks like what you might call an atomic crystal, which you might implement something known as a quantum simulator. I'll mention this later. I should acknowledge Crispin Gardner, who's in the audience, and was responsible for the theoretical prediction of this phase transition 4 years prior to it being done in this lab in Germany. So those are kind of two experiments I hope can show you sort of how exciting, how much control we have in this field, how much interesting things you can do. I'd like to say a little bit more about experiments, even though I'm not an experimentalist. So here's an experiment in theory. I stole this picture from a recent graduate from Otago from the experimental lab. This is a picture of the vacuum chamber where these condensates are made. At one end, we have all these lasers coming in to do laser cooling. Okay. Then, after it's laser cooled, the atoms are shot down to the other end, and there's a science cell where you do your evaporative cooling, then you do your science. Okay, so this is a nice picture of a vacuum chamber where this is all performed. Remember, everything's in vacuum. Nothing can touch the atoms inside this because they'll instantly destroy it. Everything else is so hot. This stuff's so cold. Here's what the experiment really looks like. Here's a science cell down this end, surrounded by huge coils. Okay, lasers coming in, high power, huge currents running through these things, water cooled. On the right-hand side, we see the laser systems. You need very precisely controlled lasers to do your laser cooling, to manipulate these atoms, to image them, etc. This is one complicated experiment. If I was to zoom out and show you the whole lab, you'd see more and more like this. So I'll emphasize, you don't go down to the shop and buy this experiment. They don't sell them in kits. You require a number of people to spend 3 or 4 years building this. These are really complicated experiments. And one of the great things about being at a place like Otago is we actually have a very strong tradition in this area, and we have a number of firsts. We're the first place in the southern hemisphere to make a Bose-Einstein condensate. That was done in 1998. That's a massive achievement, really put us on the international radar in that area. More recently, the groups obtained a degenerate Fermi gas of potassium, the first in the southern hemisphere to do that. So, of course, if anyone's interested in finding out more about this, I encourage you to ask Niels Kiergaard, who runs the lab, to give you a tour sometime. It's really a fascinating experience. And it's great to think this coldest stuff in the universe is made right here, a few blocks away. Okay, I'll tell you a little bit about parameters before going on to a little bit more about what I do. These systems are prepared in ultra-high vacuum. I showed you that. They're held in magnetic and optical traps. You can't use any material trap to hold these things. Typical numbers of atoms in the condensates could be of order tens of thousands, millions, maybe 10 millions for a large condensate. So that's really tiny speck. The density of these, the number density, is something like 10 to the 20 atoms per cubic meter. Now that probably doesn't mean much to you. That is 100,000 times less dense than the air you are breathing now. This stuff is really dilute. Okay? Everything about the system is at the extremes. The typical size is up to about 0.1 of a millimeter. So you could potentially see it if it was somehow illuminated, in addition to being really, really cold. So you might call me a theoretical physicist. I like to think I'm also quite significantly a computational physicist. And right from the early days of doing research in this area, I have always been overwhelmed by the power computers have to do things. So I remember my first honors project, getting a computer with a Pentium Pro processor in it. Probably a few people here remember this. And asking my computer to diagonalize some matrix with 100 by 100 in size, something that you'd never, ever be able to do by hand. And just seeing this computer spit up answers one after another, all these answers popping up, just being amazed and blown away by how amazing computers are at doing maths. So a lot of my work is in this area, making computers do something useful in terms of the science we want to understand. However, despite how powerful computers are, it's a little bit depressing when you come to think about quantum physics. In our regime of ultra-cold gases, the exact theory is known. It's not like in the high-energy physics where they still want to know what's happening. We actually know essentially an exact theory to describe these systems we're dealing with. So that's good, but the theory is unsolvable. Well, not in principle it's solvable, in practice it isn't. And I'm going to try and convince you that what I mean by that. Let me consider a very small condensate, 1,000 atoms in about 1,000 levels. Okay? To describe the state, to have a full quantum mechanical description of the system would require 10 to the 600 bytes of memory. Now, 10 doesn't sound like a large number, 600 doesn't sound like a large number, but trust me, 10 to the 600 is pretty large. It's possibly one of the largest numbers one would ever encounter. In fact, you hopefully won't encounter this number. For comparison, the entire world's storage, all memory, all DVDs, all Blu-rays, in 2011 was estimated to be 3 times 10 to the 20. Not even close. Every single atom in the universe added up is expected to be 10 to the 80. So even if you used every atom in the universe as a bit of memory, you couldn't store this state. Quantum mechanics is really hard theory. We know what it is, we just can't solve it for the many-particle system. Okay, in my lesson before I forgot to mention something about superposition, so I should say something now. Where do these numbers come from? Well, when you have interactions, you kind of need to mix up all these states a little bit. And what happens is, for the case of two particles and two levels, a complete description would be some number times a state of two atoms in the ground state, nothing up there, some number times all these possible configurations. And there are only 3 configurations when you've got 2 atoms, 2 states. So if one goes up to 5 atoms, 5 states, it turns out that you do all sorts of arrangements, you get 126. 10 atoms, 10 states, 92,000. 20 atoms, 20 states, 98 billion. This grows really fast. These Hilbert spaces grow massive. So for any problem we would actually consider to be serious, sufficiently large, it would just be absolutely impossible to get a direct solution. So this is kind of bad. But on the other hand, it's great for a theorist because everything we do, and even if you could solve this, what are you going to do with your 10 to the 600 numbers when you've got your solution. So as a theorist, this is great because we have to develop approximate theories that will work on the systems of interest and the regime of interest. So this is a great challenge to us. And that's what I spend my time doing, developing a theory to solve the sorts of problems we'll be interested in. And one has a range of theories one can use. I'm going to briefly outline one of the theories I've worked on. This is a very New Zealand theory, in a way I won't bother explaining, but just many of the collaborators involved in developing this over the past 10 years have been either based in New Zealand or ex-New Zealanders. Okay, so this is where the title of my talk comes from, ultra-cool matter waves. If we want to develop a theory for a system that's ultra-cold, but not actually zero temperature. Actually, zero temperature turns out to be kind of easy. We'll just warm it up a little bit. What happens when you warm it up? Well, you promote some of the atoms out of the ground state. And in fact, in this ultra-cool regime, below the critical temperature, but not zero temperature, you'll find there's a reasonably large number of levels in the system where the average occupation is greater than 1. It turns out, for all of those levels, we can stop thinking about there being occupational particles in those levels and replace them by matter waves, these things that interfere and behave in a sort of interesting way. So this is great. We take a massive problem in Hilbert space, was completely unsolvable, and for those levels end up with a nonlinear wave equation in 3D space. Very easy to say, but the sort of ideas underlying this were developed in a huge number of papers over 10 years involving both myself and my collaborators. This turns out to be a very useful and flexible theory. I can't go into it in too much detail here, but I'm of course welcome afterwards anyone to ask me some more details, but I'll show you what it can do. Here's a very nice picture generated. The picture in the middle is what we can simulate using these kind of theories, looking at the velocity distributions at high temperatures, just below condensation, and all the way down to zero temperature. And this compares very nicely with what's done in experiments. So these are sorts of things we can calculate the quantum many-body problem in a very tractable way. Just for reference below, I've shown these what the actual pictures look like of these instantaneous matter wave fields we use in our solutions. So what sort of problems can we deal with? Again, I'll just give you a brief little touch upon the sorts of physics we've looked at in this system. One particularly important thing is what you could call the quasi-two-dimensional Bose gas. And this system is kind of interesting for the following reason. If I take a three-dimensional Bose-Einstein condensate and start squeezing it down, as one can do by, for instance, putting it in a one-dimensional optical lattice, just slice it up, something interesting kind of happens. It turns out there's a theorem of many-body physics which says that a condensate is not allowed to exist in 2 dimensions. The fluctuations will kill the condensate. Well, that's kind of depressing, but superfluidity remains. There is no condensate, but there's a superfluid. So 2D is a really interesting playground for many-body physics. And this superfluid is kind of unique because lying under the superfluid is the role of something known as vortices. What is a vortice? Well, it's like a whirlpool taken down to the quantum level. And at the quantum level, there is a fundamental unit of circulation, and these vortices can either be positive or negative, circulating left or right. And in the superfluid, these vortices tend to bind up into pairs. And so this is a novel known as a Berezinski-Kostelis-Stellis BKT superfluid phase. This is something we can look at with our theory, and unlike any other available theory, we can look and see what the vortices are doing. This gives a really unique window of studying this very interesting superfluid regime. As another kind of example I've shown here of a non-equilibrium sort of dynamics we can consider with our theory is we can set up the superfluid equivalent of a persistent current. So in our condensate, we put a whirlpool in the center. I'll show this. Here's a quantum whirlpool through the center of this. This current should persist, except that it is in a non-rotating system with a thermal cloud. And over time, this persistent current will wander away from the center of the condensate and die. And important questions remain about how long that takes. This is a non-equilibrium challenging problem. And these are the sorts of things we can study with this theory, and I'll acknowledge Sam Rooney is a very important person for doing work in this area. So these are the kind of things we can look at, play with, post some results, and ask our experimental cousins to go and have a look and verify this. So this is all very fun. Extremely cold temperatures, a very novel fluid. You may ask yourself, why should we study ultra-cold gases? Well, I'll give you the standard why I'm interested in it. These are very clean, flexible, controllable, and isolated systems. Okay, many systems where you can look at quantum mechanics, you get given what nature gives you, some solid lump of material, and you just have to analyze it. You've got no ability to change it. But here is a system which we know essentially everything about, and we can study and manipulate it. There's this opportunity for direct comparison with theory. You can do the experiment, I can do the theory, hopefully we agree. But often there's some challenge in there. So it's very easy to try and make comparisons between theory and experiment, and there's lots of challenges between the two fields. And so there's a sort of dream it up, and they will or might try it. So we're always trying to come up with novel ideas saying, experimentalists, go out there and try this. So it's a very nice field to work in for that reason. As far as technology goes, one of the reasons, some of the reasons you might be interested in this field is leading to improvements in technology such as atomic clocks. And so this graph at the top shows basically the accuracy of atomic clocks versus time. There's quite a significant jump in the middle of the 1990s when laser-cooled clocks came into play. But one expects as more and more technologies developed in this area, we'll get better and better atomic clocks. Why do we care? Things such as the global positioning system depend on us having these very precise atomic clocks. Other areas of precision measurement, the fact that you might be able to develop something like an interferometer, instead of being based on lasers and light, this interferometer could be based on atoms and allow very high precision measurement of things such as magnetic fields, gravitational fields, and the like. But there's some really exciting reasons which I think we'll uncover more during the century. Idea of a quantum simulator. So there's a picture here of Richard Feynman, a very famous, charismatic American physicist, and there's a quote of him. Now, Richard Feynman had this bold Brooklyn accent, which I can't hope to emulate, but he said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy." What Feynman is saying is, I stated earlier, quantum mechanical problems are hard. These massive spaces, which we can't ever hope to directly solve on a classical or computer you can buy at the shop. So quantum systems are really hard to simulate. But what he's suggesting is that if we had a controllable quantum system, a system that obeys the laws of quantum mechanics, maybe we could use that to simulate some system we can't understand. So we actually use quantum mechanics to conquer quantum mechanics. This is the idea Feynman came up with. And let me suggest to you there are big opportunities for this, and there's a lot of work going on in this direction. So here is a hard system. This hard system, this is a unit cell of yttrium barium copper oxide, a cuprate superconductor. Now, I showed this graph earlier showing the critical temperature of superconductors versus time, and in the 80s we had this huge jump when the cuprates came around. They're known as high temperature superconductors. High temperature because it's only negative 150 degrees Celsius. Okay, so the problem is we don't understand how they work. The theory for these systems is too difficult. There's lots of competing theories, but basically the jury's out. We don't understand how these work. We cannot simulate them. They're too complicated. So that's a really hard system. Maybe we can take one of these controllable systems, our atoms in a lattice, do things to these systems to understand this very hard problem. If we could work out what ingredients of that system make it a high temperature superconductor, maybe we can make an even higher temperature one that operates at room temperature. These are huge, huge goals for the field in the long run. There are other such problems, very difficult quantum mechanical problems, design of new drugs, things such as understanding photovoltaics, better ways to produce and understand these. Often these problems reduce down to very hard quantum mechanical problems. So if we could have to ourselves a controllable quantum system, or maybe you want to call it a quantum computer, I think it's a very exciting future. This field keeps expanding and developing new things that keep people excited. And one of the things is there's always new ingredients coming along. I could talk for hours and hours, but I won't, about some of these. I've put two in boxes because they're systems I work on. The fact that new ingredients were turned up through new atoms or species people are looking at, long-range interactions in these systems, dipole-dipole interactions, liberating the spin degrees of freedom of these systems to study some combination of magnetism in these superfluid systems. So that's exciting new sort of knobs to twiddle on these systems. The ability to make synthetic magnetic fields. These are neutral atoms we're dealing with, but you can make them think they're seeing a magnetic field and think they're charged. Okay? You can confuse these atoms. You can associate atoms into molecules and make molecular gases. So this is chemistry done not driven by entropy, but driven by control from external fields. So this is all these are all being done in the lab and allow this system to have lots of flexibility. Okay, so at that point, I'm in the end part of what I'm talking about, but I'm not finished saying some things. So I'm in my end game, and I want to make a statement about teaching and a few acknowledgements along the way. One thing I'd like to say is, about 8 years ago, our department repealed Don't Ask, Don't Tell. We provided these devices to our students in first year, and for me, this was really a revolution in teaching. Prior to that, I was in the situation of like I am tonight, information flowing out, not being able to tell from the faces if I was boring people, they didn't understand, or whatever. And what this technology did was allowed one in the lecture to have this real-time input from the students. What do they know? What do we need to spend more time on? But actually the revolution was when the students got to see that they weren't the only one who thought that way, the discussion that opened up in class was really eye-opening to me. And so I'll congratulate our department for going down this path. When it did, it was a really bold move. And as I say, it really affected the way I've done teaching ever since. So I just wanted to mention that because I spent a lot of time teaching and this was something important. I've made a list here, and I really hope I haven't left anyone off, of the most important people in everything I do. There's the members of my group. I've listed from MSc level and above. Honour students, you stick around and you'll make it next time. I have had the fortune of working with a lot of really great talent, and both postdoctoral and student level. I would say we're very fortunate here in New Zealand. We have a good education system. I never seem to have a shortage of very talented students coming through. In fact, I have colleagues from very famous institutions overseas who are very jealous of the quality of the students I get coming through. So I would just like to acknowledge these people. I think working in my area is very difficult. You work on a project basically by yourself. You have to understand all the literature in that area, develop theories, develop codes, and I mean write your own numerical codes to solve problems. This is a very demanding area, and I have benefited greatly from these very talented people, many of whom I would rate as being far more capable than myself. I'd like to thank my department. I put photos of my 3 HUDs I've served under. I'd like to thank, of course, Jerry Carrington, man of great wisdom who appointed me in the first place. Rob Ballard and Pat Langhorne. Now, I would like to say I think the physics department is a very progressive department. Right from when I arrived 10 years ago, there were workload models in place. Everything was very transparent in our department. The department worked very hard to protect new staff members from too much work early on so we could get our research careers going. I think it's a very progressive and supportive department of everyone in it. And so I would like to publicly acknowledge the great leadership we have had, and I hope the university realizes what a great unit they've had there. I've decided not to list members of academic and general staff in our department. You're all wonderful, but I'm just scared I'll forget someone. There's lots of great people, a very collegial department, and it's been a pleasure to work in this department over time. I'd like to say something about quantum research in New Zealand. I've put some photos of important people. In the background, you can see Rutherford. Rutherford is undoubtedly the greatest scientist New Zealand ever produced. Okay? He got the Nobel Prize for chemistry, but things were a bit different back then. But I put him in the background for the following reason. Rutherford went away to do his work. He did his work overseas. These 4 people in front of you established quantum physics in New Zealand. They did their work in New Zealand, and they put us on the international stage. I think New Zealand has punched above its weight in quantum physics for a long time. Maybe it's not widely known. Often these things are not widely known outside of the circles. And so I would like to pay respect to all these people. In particular, Rob Blair, who has worked tirelessly to build up quantum physics at Otago. We have 8 permanent faculty roughly in this area, and that is a really hard thing. This is a very competitive area internationally. It's hard to get good people, and so Rob has tirelessly worked to develop a department and get us critical mass and an international profile. So thank you very much for all that hard work, Rob. I know at times you feel like pulling your hair out, but you've made something wonderful. I've also crossed my fingers at the bottom. In conjunction with our colleagues in Auckland, we have a current Centre of Excellence bid in. David Hutchinson has put a huge amount of work putting together a fantastic application. Maybe we'll have good news in the next couple of weeks. David, fingers crossed, thank you for all your hard work. University and funders. I've benefited immensely from support from the Marsden Fund. It enables one to follow this sort of fundamental research that we get to follow here, and so I would like to thank them. My university is a wonderful place to work. It has supported me in many ways. Postgraduate scholarships are just a wonderful thing, and it's great that they're so available here, also through UORG funding, etc. I would also like to acknowledge something I think is very unique about Otago. Our Vice-Chancellor, our Deputy Vice-Chancellors, our Pro-Vice-Chancellors are all highly successful academics. They lead us by a do as I do, not a do as I say approach. And I think that the sense I get around me is that we always respect our leaders a lot because of that. I think Otago has resisted all sorts of corporate trends that have gone over other institutions and held up high academic values. And so I thank our leaders for protecting us and keeping this a wonderful environment to work in. Finally, I have a life outside of work. Luckily, these 2 lads, well, I'm not sure I saw the other one, but anyway, one of them I can see, and he's survived the whole lecture. I think it's at times hard to be a family of an academic. One never really stops working. Almost never do I go anywhere without my laptop. I'm traveling a lot. My hours are very irregular. And so life is often very hard. I travel a lot. Furthermore, it's hard, even harder being part of a physics family. We bring physicists home, and that's always... So sorry about that. So in particular, I'd thank Bea. She followed me to the United States. I did my postdoc and then came back here. So I've always sort of been developing my career, and Bea's taken a support role when needed, and of course through all the stressful things related with raising a family. So thank you very much, Bea. I appreciate your support. I couldn't have done it without you. And I think at that point, I'll say thank you everyone for coming. The end.
Blair, thank you very much. I'm Pat Langhorne. You might have seen my photograph, a much younger photograph, up on Blair's slides there. I'm currently the head of department in physics, and it's my privilege to be around all these very smart people. I don't know, some of you will have been in Blair's office. I know some of you have, but if you go into Blair's office, up on the wall, there's a great big TV screen. And you might be tempted to think, lovely, I'll just sit down in one of these comfy armchairs and I'll watch an episode of Coronation Street or Downton Abbey or something. But if you look at that, what you'll see is a whole lot of formula, very big, long formula that Blair and his students converse in. And so I think we've been very privileged today to have been taken beyond these formula and had that world that the formula tell you about brought very vividly to our sight. So very vividly to what we can see. And of course we see that it's a very strange world, this very cold world where everything's going very slowly. You know, you might be tempted to say, nah, go on, Blair. You're pulling our legs. It can't really be like that. But I think we've got to remember that it is reality. I mean, it's as real as pencils. It's as real as a tax return. It's as real as anything else around us in this room just now. So I'd like to thank Blair very much for bringing this all to our view. I'd also like to just add to what the Vice-Chancellor and Pro-Vice-Chancellor said about Blair in the introduction. What they didn't say is that he's actually a damn nice person, as well as all the other great things that you can say about him. And so we are delighted that he's now Professor Blair, and we would like to present him with this token of our appreciation. And finally, we'd like to invite you all to join us for drinks and nibbles over at the staff club. So if you follow the trail of people, it should take you upstairs in the staff club. So thank you, Blair, once again. We are very delighted with your rise to this elevated position, and it is very well deserved.